Now, the reason I wanted to prove this little result is because it simplifies the proof of the thing that I really wanted to prove. And that is this. The first time I read about what I'm about to say, it was worse than bamboozlement. I just thought that there had to be some kind of mistake somewhere. So one can show that the number of points on a line equals the number of points on a square. So there are as many points here as there are there. Not just the edges, but the entire area of the square. And here's how we're going to prove it. So a useful way of thinking about the points in the 0, 1 interval is just as sequences of that form. So everyone in there has a description of that kind. And the points in the square are just pairs of sequences of digits of this kind. So the way I'm going to prove the result is by first thinking not about the points themselves, but about just their notations in this base 10 way of writing things out. And then there's a little annoying problem, which is that, as we've seen, there are points in there that have more than one notation. So for example, the half point there can be written out like that, or like that. So we're going to have to do something to correct that problem. But what we're going to do is we're just going to use this trick. That's what I wanted to prove. OK, so what I invite you to do is to forget about the complication that I just mentioned and just think that what we're showing is that the set of sequences of this kind is in 1-1 correspondence with the set of pairs of sequences of that kind. So I'm going to write that out. So let the set S for sequence be the set of sequences D1, D2, D3 for these digits. So S is just the set of infinite sequences of digits. And what we're going to show is that the cardinality of S equals the cardinality of its product. And showing that is amazingly simple. Can anyone think about how to do it?
To go from S to S cross S, however you say it, you take like every other digit of S and you like make it one thing and the other one's in, yeah. And to go backwards, you can do the same thing. You like spread them up and then do that. You can explain that better now.
Exactly. Yeah, so let's do it the reverse way you mentioned, because I think it's slightly easier. So we're going to take a function f that takes us from each element in there to an element in there, and which is 1-1 correspondence. So what f does is we give it a member of S cross S. So in other words, a pair of sequences, two sequences, and it delivers this sequence. We just take the first element of the first one, followed by the first element of the second one, second, third, fourth, and so forth. So now let's check that it works. So we need to see to check that it works is first that this function is defined for every element of S cross S. And of course it is, because whatever two sequences you're given, the result of alternating those sequences is going to be well defined. It's also unique. So if you're given two sequences, there's only one sequence that can result from alternating. OK. Then the next thing we need to check is that using that technique, you hit everyone in here. But of course you do, because everyone in here is going to have some sequence. And that's going to result from alternating two sets. Which ones? Well, the one that consists of all the odd entries and the one that consists of all the even entries. So our function goes from here to here. It's 1, 1, and it's unt. Now I'm going to correct the little problem. And don't worry if you don't understand this. So think of it as I've opened a parenthesis. I'm going to very briefly say how it works, and then I'm going to close the parenthesis. So parenthesis open. We get a problem because S and S cross S aren't really 0, 1 and 0, 1 cross 0, 1. You have some extra things in here because you have two different sequences. For example, that sequence and that sequence that correspond to the same point up there. But that is not something we need to worry about, because the only case in which that can happen is the case in which we have some number in there which has a decimal expansion ending in zeros or ending in nines. All of those numbers are rational numbers. And we proved last time that there are as many rational numbers as natural numbers. So that means that our set of problem cases is just a countable set, which means that we could just use this theorem to show that the result of adding problem cases doesn't change the cardinality. So the way we solve our problem is we first show that if you go from that interval to S, you preserve cardinality. Then we show that if you go from S to S product S, you preserve cardinality. And then we show that if you go from here to there, you preserve cardinality. So you preserve cardinality if you go from the line to the square. Close my parenthesis. And notice that this result generalizes. So we could use the exact same procedure to show that there are as many points on a line as there are points on a cube or a hypercube, or I didn't even know the notation after that, like a hyper-duper cube. In fact, you can even do it for the analog of that in countably many dimensions. And by using Rose's observation that you have as many points in there as you have in there, you can extend these results to not just line segments and squares and cubes, but the entire line, the entire space R2, the entire space R3, the entire space R4.